Assalamualaikum and a very good day to everyone. We from CS1102A Group 3 have prepared this video presentation for Miss Nurbayah Awang.
Assalamualaikum. My name is Muhammad Azim Aidil bin Manu Azmi, student ID 2023140663, and I'm from class CS1102A.
My name is Muhammad Adhan Fitri bin Kamaruddin. My student ID is 2023644943 and I'm from class CS1102A.
Assalamualaikum warahmatullahi. My name is Ada Hafiz Ibrahim. My student ID is 2023148209. I'm from class CS1102E.
My name is Ahmad Shafi'i bin Adnan. My student ID is 2023148147 and I am from class CS1102A.
The topic that we want to present is topic 3 from Calculus 1, which is application of differentiation. What is differentiation? Differentiation is a process of finding the derivative or rate of change of a function. There are few applications of differentiation, which is number 1, related rates. Number 2, analysis of a function. Number 3, apply maxima and minima. And the last one, mean values theorem.
So let's go to the introduction of related rates. Related rates problems in differential calculus have two or more variables that change simultaneously, possibly at different rates. The rate of change is usually with respect of time. For the question 1, ores is flowing out from a vessel and forms a conical pile on the ground. The height of the cone is 3/4 times the radius of its base. If the radius of the base is 200 cm and the volume increases at rate 10,000 cm, find the increased rate of radius of its base. From the question, we can identify that dV over dt is equal to 10,000 cm, height is equal to 3/4 r. Since we don't know the value of dr over dt, so we just put a question mark here. For the formula, since it's all about cone, so the formula that we use here is 1/3 pi r square h. For the step 1, substitute the value of h in the formula. So we get v is equal to 1/3 pi r square in bracket 3/4 r. So we can simplify it. We get 1/4 pi r to the power of 3. For the step 2, differentiate and respected both sides with time. So by that, we will get dv over dt is equal to 3/4 pi r square dr over dt. So for the next step, put all the value in the equation and simplify it. As we all know that the value of dv over dt is equal to 10,000 and r is equal to 200. So the equation that we get here is 10,000 is equal to 3/4 pi r 200 square dr over dt. We can simplify it, so we get 10,000 is equal to 30,000 pi dr over dt. So for step 4, place dr over dt to the left to get the value. So here we get dr over dt is equal to 10,000 over 30,000 pi. So for the final step, we can simplify it. By that, we will get dr over dt is equal to 1/3 pi. So the final answer for the question is 1/3 pi.
This question is about a person standing at the end of a pier above the water and is pulling in a rope attached to a robot at the waterline at the rate of 2 meters per minute. How fast is the boat moving in the water when it is 12 meters from the pier? With that, our first step is draw the diagram and label the dimension. As you can see, I label the pier 5 meters from water as x and the waterline at the rate of 2 meters per minute as r, and the length from boat to pier is 12 meters as y. For step 2, find the related formula. If you are look at the diagram, the shape is almost look like triangle. So we are gonna use the x squared plus y squared equal to r squared formula. We already got the value for x and y, which is 5 and 12. So we need to substitute all the value into the formula to find r. Then we got 13 for r. After that, for step 3, use the formula again and differentiate the formula. After the differentiate, we got 0 plus 2y dy over dx equal to 2r dr over dx. And then for the last step, substitute all the value and solve it. With that, for the final answer for this question is 13/6 meter per minute.
So to conclude for both questions about related rates, in both cases, the relevant rates concepts are utilized along with formulas to illustrate the correlation between variables and the process of solving for the desired rates. In the first instance, the issue was the increasing radius of the conical pipe, and in the second, the issue involved a person pulling on a rope that connected the boat's movement in the water. Powerful tools for analyzing changing amount in a variety of real-world circumstances are calculus and associate rates.
Introduction to apply maximum and minimum problems. It is also known as optimization problems. It is used to determine maximum or minimum value of a function within the constraint. The maximum value is called absolute maxima, while the minimum value is called absolute minima. In real life example, it is used to maximize the profit in a company or to calculate the least amount possible material needed to build something.
In this slide, I will be presenting about to solve apply the minimum problem. As we can see, the question 3, 4 meters of wire is to be used to form a square and a circle. Find the dimension for both the square and the circle that will minimize the total area. Then determine the minimum area. So step 1, we have to sketch the wire. The wire is 4 meters long. So from the wire, we use it to form a circle and a square. So we have to sketch a circle and also the square. So the square, the width and the length are same. So from both the square and the circle, we have to find the dimension. Then minimize the total area. After that, we have to determine the minimum area. So after step 1, we can go on with the step 2. But before we go with the step 2, we have to know the area and the perimeter for both square and the circle. So area square equal to a square. We get it from width times length. Then perimeter square equal to 4a, which is 4 times a. The area circle equal to pi r square, and the perimeter circle equal to 2 pi r. So in this case, we use the step 2. So first we have to find the equation for perimeter total. So perimeter total equal to perimeter square plus perimeter circle. As we know that perimeter total equal to 4, so 4 equal to 4a plus 2 pi r. So we simplify it until we get the a equal to 1 minus pi r over 2. Then after that we use the equation to substitute into the equation for total area into make it only one variable, which is r. So to find the equation for area total equal to area circle plus area square. So pi r square plus a square. Then we substitute the a with the equation perimeter total. So it will be pi r square plus 1 minus pi r over 2 square. Then we have to factorize it. Then it will be 1 minus 2 pi r over 2 plus pi square r square over 4. Then the 2 pi r over 2, we can simplify it until it get pi r square plus 1 minus pi r plus pi square r square over 4. So after step 2, we're using the step 3, which is to find the first derivative. So to find the first derivative, we're using the area total equation, which is pi r square plus open bracket 1 minus pi r plus pi square r square over 4 close bracket. Then we differentiate it, and it will be 2 pi r minus pi plus pi square r over 2. Then we equate it with 0. Then it will be 2 pi r minus pi plus pi square r over 2 equal to 0. Then r it will be 0.2800. Then we're using the step 4, which is to find the second derivative and substitute the value of the dimension from step 3 to it to determine whether it maximum or minimum value. So first we have to differentiate 2 pi r minus pi plus pi square r over 2 to get the second derivative. So second derivative is 2 pi minus 0 plus pi square over 2. So we will get the minimum value is 11.2180. Then step 5, to find the value of other dimension, which which is we're using the perimeter total equation, which is A equal to 1 minus pi r over 2. Then we substitute the r with 0.28. Then we will get the value of other dimension, which is A equal to 0.5602. Then step 6, to find the minimum or maximum value. So we're using the area total equation, which is pi r square plus 1 minus pi r plus pi square r square over 4. Then we substitute the r with 0.28, and also we will get the 0.5601 m squared. So this answer will conclude for question.
This question is about applied maximum problem. The question is a mirror in the shape of a rectangle with an equilateral triangle attached to the top is to have a perimeter of 250 cm. Let x be the size of the equilateral triangle. A. Show that the area of the mirror is given by this equation, and B. Hence find the dimension that will maximize the area of the mirror. So the first step is to draw the diagram and label the dimension. Since it is an equilateral triangle, all sides will have the same value, which is x. And for the rectangle, we have two lengths and one width. As the bottom of the triangle and the top of the rectangle is connected, we'll make the width at the bottom become x. Again, in A, we will be using the second step, which is to find the equation to be maximized in one variable. So in this case, we can find the perimeter by using the p equals to 2x plus 2l plus w, and substituting the w with x, we will get the p equals to 3x plus 2l. And since the total of the perimeter is 250, we can substitute in and make it in terms of L, since the equation in the question does not have L. And we will get L equals to 125 minus 3 over 2x. The area of the rectangle is given by width times length, which will become x times the L in the above. And the final equation is 135x minus 3 over 2x square, and the area of the triangle is square root of 3 over 4x square. Area of the mirror is given by area of the rectangle plus area of the triangle. So in order to simplify it, we will have to time the denominator and denominator with 2 to make it equals to 4. And after that, we can simplify it to make it similar to the question. So the equation is shown. We will be using step 3, which is to find the first derivative and equate if 0 to find the value of x. The first derivative of the formula is 125 minus 2 bracket 6 minus square root of 3 over 4 bracket close bracket x. And to simplify the equation, 125 minus 3x plus square root of 3 over 2x. And then we equate if 0, and then we will get x equal to 58.567161. After that, we will have to use step 4, which is to find the second derivative and substitute the value of from the x from the step 3. So the second derivative is negative 3 plus square root of 3 over 2. As we have no x, we will not substitute and only do the equation, and we will get negative 2.1340, which is maximum. And for the last step, which is step 5, is to find the value of other dimension. From A, we get that L is equal to 135 minus 3 over 2x. By substituting x with 58.5761, we will get that L is equal to 37.1359, which concludes for the B. In conclusion, apply maximum and minimum problem requires solver to be able to imagine, draw, and label the shape of the object in order to eliminate unneeded side and be able to manipulate the formula into one variable so that differentiation is possible to get the answer.